we've introduced the concept of Riemann sums, but it's nice to formalize it. So if we're going to take an arbitrary function f, and if it's defined on some closed interval ab, then what we can do is we can define what's called a partition, and we're going to call that partition delta. So deltas be a partition of this, and the formal definition says that your left endpoint a is equal to some x0, which is less than x1, less than x2, less than da 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 xn minus 1, which is less than xn, which equals b. Which is nice and all, but a more practical understanding is to take the number line and say, all right, I have a starting point A and I have an ending point B. And my starting point is x0, or sometimes people say x naught or even x aught. And then xn is my last point. And then I have some ordered values in between. And none of those values can equal each other. That's why it's strictly less than. But the distance between values doesn't have to be uniform. So I have a decent gap here, but a tinier gap, a bigger gap, a really big gap, a small gap, a really big gap. So as long as you just have a sequence of points, you're creating, again, it's a partition. If you think about partitions, it's just slices. So what I'm creating is a bunch of subintervals that are all kind of stitched together to form the real interval. I'm creating small slices. And I'm doing that because these are going to be those widths of the rectangle. And then we'll figure out what the height is in a second. So what we're going to do is we're going to describe each of those widths as delta xk. So that's going to be the width of the kth subinterval. So it goes from the xk minus 1 to xk. So let me get a marker here. So that means that would be, that would be delta x1. This would be delta x2, delta x3, and then delta xn. And that's all that's saying, is that that's the width of the subinterval. And then the width there, and for what we're doing here, the width is really just the new x value minus the old x value. I don't know why they overcomplicate it, but if you do more advanced mathematics, that width is not quite as simple as that. So they're trying to use more general language when discussing this idea of width. But just know that for our purposes, what we're trying to do right now, it's literally just this number minus that number, right? Because the width of that interval is just that number minus that number. It's just the length. Anyway, now here's the real interesting thing. If I take some point, any point in the subinterval, so if I'm here, I could take the left endpoint, I could take the right endpoint, I could take some random number in between anywhere. I could take the exact middle of those two endpoints. I could take, 1/3 of the way. It doesn't matter. It has to be in that subinterval, but it doesn't matter where in that subinterval. So you can, strictly speaking, if you have to do this from a theory standpoint, it has to work on any of them. So you may try to do a Riemann sum, and for some reason it actually works on the left subinterval, but it fails on the right subinterval. So you have to be careful. But for our purposes, what we're trying to do, what you're going to do is pick a convenient one. Generally speaking, you're going to pick the left, right, or exact middle. Those are always great choices. So if we take one of those points and we evaluate the function at one of those points inside the subinterval, and then multiply it by the width. Again, we have a rectangle, so this is a rectangle, and this is the sum of those rectangles. And that is what is called a Riemann sum of f for delta. So delta being that partition, Riemann sum of f for delta. Now, there's a little bit of extra technique here, which is that the width of the largest subinterval, the width of the largest subinterval is denoted by this. It's these two straight lines mean norm. If you go into things like linear algebra and whatnot, you'll see that notation to indicate like a distance or a width. it has this notion of magnitude. Anyway, so that width of the largest subinterval is denoted by this, and it's called the norm of delta. So over here, if this was x4, we don't know, but if this were x4, then this would be the width of that delta because it's the largest one. It wouldn't be this one because that's the smallest one, or actually this one probably smaller, but this is very large and this is also very large. So whichever one's the largest, that's known as the width of delta. And so the reason we want to do that is it's important to understand how small those are. Like there are some small pieces, but what's the chunkiest piece I got? Now there's another little piece, which is that if the partition is what's called regular, what that means is that all of those spacings are equal. And that's kind of an ideal scenario because then your delta x k here doesn't have to be like figured out. It's always the same length, and that's just the width of the entire subinterval or the entire interval divided by n, right? If I've got two pieces, it's just the width divided by, or it's just the total width divided by, or the length of the interval divided by 2 because it's in two chunks. If it's in three pieces, it's the length of the interval and divided by 3, and so on and so forth. This is a really nice case. This is an ideal case. Now, it's important to note that the width is always actually greater than or equal to this. This minimizes the width of the subintervals, or it minimizes the width, or it minimizes that norm of delta. Because otherwise, if you have if it's uneven, you'll have some pieces that are smaller than this and some pieces that are larger than this. So since this always cues on the larger piece, you just can't get around it. So this is kind of a lower bound for this value. Why does that matter? Well, if we're going to take the Riemann sum, when we do these Riemann sums, we want to add more and more rectangles. So we should keep adding and keep adding and keep adding, which means that width has to shrink smaller and smaller and smaller. Because if I'm going to keep adding values, it's got to shrink smaller. We want to shrink this whole thing. We don't want to cluster up a bunch of points over here and not touch this, because I've still got a lot of error if I don't do that. So I want to keep adding values and values and values. Well, if that's true, and this is kind of the lower bound, if this value is shrinking down to 0, the only way for this term to shrink down to 0 is for n to go to infinity. So basically what I'm saying is that if you're trying to shrink that width, that norm value, if you're trying to press it down, the only way you're going to do that is by adding points, which makes sense. How else would you do it? But it's pretty standard, especially in the regular case. You just kind of note that the limit as n goes to infinity of this thing. That's clearly going to go to 0 because that's just some number divided by n. So anyway, this is the formal definition of a Riemann sum and what's going to be known as kind of a Riemann integral that we're going to get to. And it's extremely powerful. It's hard to impress upon you right now how important it is, but there's a lot of richness there that you'll probably come to appreciate, maybe not for a long time, but at some point in your life.